is Ray Zhou, who's an associate professor in the Center for Actuarial Studies at the University of Melbourne. She received her PhD in actuarial science from the University of Waterloo. She's fellow of the Society of Actuaries. Her research focuses on stochastic mortality modeling, longevity risk management, and innovative solutions for weather and climate risk. She's been publishing in leading actuarial journals such as the Journal of Risk and Insurance, Insurance Mathematics and Economics, and the North American Actuarial Journal. And she's going to speak to us today about model risk in pricing wind speed derivatives.
Okay, can everyone hear me well? Yes, okay, good. Thank you, David, for inviting me to the workshop and for the kind introduction. Today I'm going to talk about model risk in pricing wind speed derivatives. This is joint work with my PhD student Giovanni Grazianti, Professor Johnny Lee from Waterloo, and my colleague Xueyuan Wu from Melbourne. Well, here's the plan for the next hour. So I will briefly talk about the background and motivation behind this work, and then I'll introduce the wind speed derivatives. Then we will move on to the two key components of pricing wind speed derivatives. The first is the wind speed modeling, and the second is a pricing method. And finally, we're going to look at the pricing results and conclude. Okay. So wind is a clean and free source of energy. As the global effort of reducing carbon emission has ramped up in the recent years, the global installed wind power capacity has been growing really fast. So in 2016, the capacity was 486 gigawatts, and in 2020, that is 837. So just go into the next page. If you look at the percentage of the average annual electricity demand covered by wind in 2021, in EU and UK, about 15% of the power is covered by wind. But if you look at individual countries, well, for example, the top one, Denmark, 44% of electricity demand is covered by wind. So that's a very significant amount, right? And the dark blue is onshore wind farm, and light blue is offshore wind farm. Oh, not this one, back. So we can see that the wind power is gaining more share in the electricity market. Well, wind power production is determined by several factors. The most important three are wind speed, air density, and blade radius. When we have higher wind speed, the blades will rotate faster, generate more energy. The denser air will exert more pressure on the blade, so it will generate more power as well. The larger blade will move more air, capture more energy. So these three are the most important. But the wind is very beneficial. At the same time, it comes with challenges. The wind is highly intermittent. We cannot store wind to meet future demand. Well, if you have a huge battery, you can do that, but that's our technology is not there yet, right? So the uncertainty in wind power production is undesirable for wind farms and energy companies. That's why we want to manage the risk. Now, a bit about the wind derivatives. Derivatives on wind indices usually have payoffs linked to wind conditions or wind power production. These derivatives are developed to mitigate the revenue uncertainty arising from the variability of wind speed. So it's volume risk here we're talking about. We're not trying to manage the price risk. There have been a couple of wind power futures traded on exchange. The first is the wind power future traded on European Energy Exchange. The underlying index is the average load factor. So that is determined by the ratio of the actual power produced and the installed production capacity. I will talk about the capacity a little bit later. Okay. So this one, if you look at this future, it's dependent on the actual production amount. Okay. And the second wind derivative is the wind power future currently traded on NASDAQ. It's written on the German wind index, NRXY. This index is a synthetic one, so it's not about the actual production. It's actually calculated based on weather conditions and power curves of wind turbines. So in a sense, it's actually more transparent. When you have the actual one, you don't know which turbine has been shut down or broken. But using the synthetic one, you know exactly when I have this weather condition, when I have certain turbine power curves, I know exactly what the derivative index would be. Yeah. It's highly transparent. The parameters of the power curves are made available to the market participants, and the daily settlement prices are determined using established weather forecasting models. Well, pricing is obviously very important for the development of this kind of product. There are two components in order to price the derivative. First, we need to understand and predict wind conditions. The second is a pricing method. First, let's talk about how do we model wind speed. Well, there are two types of models. You can use meteorological models, or we can use time series models. Well, meteorological models reproduces the physical phenomena, so it's quite complex, requires lots of computation. It's very good for short term. On the other hand, time series models, a lot simpler. It's good for capturing the historical trend and pattern. It's usually not so good for very short term. By short term, I mean like a 1 week, 2 week time. But it works pretty well when you're looking at the medium term over 2 weeks to long term. Okay. So here, since our wind power futures usually have delivery period that's more than 2 weeks, it can be up to 3 years. Our focus is more on the medium to long term. So that's why we chose to use the simpler time series model here. And there are lots of features. When you look at the wind speed data, you'll see seasonality, you'll see zero correlation, and you will also see the heteroscedasticity, which arises from two sources. One is the seasonality, and the other is the volatility clustering. We'll see that later on. In addition, you will also see positive skewness and excess kurtosis. Right. So if you look at existing time series models for wind speed, they usually only consider a subset of these features we listed here. So our goal here is to build a model that's able to capture all these features I just talked about. In terms of pricing, it's quite challenging because we know that wind speed is not a tradable asset. Okay, you can trade the future on it, but itself it's not an asset, right? Also, the complex dynamics of wind speed implies market completeness. The market incompleteness means that if you are trying to use risk-neutral pricing, you will have an infinite number of risk-neutral measures, and you need to decide which one you want to use. Okay. So there have been several pricing methods developed for wind derivatives. Risk-neutral is the most popular. Researchers have used Gersenov theorem, they have used Escher transform. For the risk-neutral pricing, there are some other methods, for example, equilibrium pricing, good deal bonds. The problem with existing pricing literature is that they don't consider stochastic volatility. We've found the stochastic volatility, like volatility clustering, very significant in the wind speed data. So we will try to fill that gap there. And most of these pricing literature assume normality, which is not true in most cases. Okay. So our contribution, 3 contributions. The first is that we try to develop a stochastic wind speed model to capture the features I just talked about. And we consider 2 models. One is parametric, the other one is semi-parametric. In the parametric model, we will use generalized hyperbolic distribution to allow for the skewness and kurtosis. So we want to look at alternatives to the normal assumption. In a semi-parametric model, we're going to use bootstrap in the simulation of future wind speed. We also propose pricing methods suitable for the wind speed model we developed. Okay. So we're going to apply the conditional Escher transform or change of measure. And for the parametric wind speed model, we are able to express the risk-neutral wind speed dynamics explicitly. We also have a pricing method suitable for the semi-parametric wind speed predictions. And the final part is the model risk. We're going to look at the model risk in pricing wind derivatives. We will consider both future and options written on two types of wind speed indices. We'll look at how the choice of wind speed model would affect the derivative price. Okay. First, wind speed derivatives. A bit of basic knowledge about wind power. Okay. So we obtained our wind speed data from the German weather service. So we're going to use the data from a German weather station. This wind speed is collected by weather transmitters located 10 meters above ground. But wind turbines are usually a lot higher. It can be as high as 170 meters. Well, when you're at a higher place, the wind would be stronger. So how do we go from the wind speed at the 10 meter above ground to wind speed at the turbine height? There is the power law that's usually used to do the approximation. So this is the power law here. W here is the wind speed at the turbine height. So the turbine height is H. V is the wind speed at the station height. Station height is S. Okay. We are going to use S equal to 10, H equal to 90, so turbine height is 90 meters. And the A here, this here, A, is the power law exponent. So this value will vary with atmospheric conditions and land features. Well, A, here we set A to 0.125, which is suitable for open farmland. So if you're looking at offshore wind farms, which are installed over the ocean, then you would expect A to be larger because there are stronger wind on the ocean. As you can see that the taller the wind turbine is, the stronger wind would be. Okay. And well, we've just talked about wind speed largely determines, is one of the most important factors that determine the amount of electricity generated by a turbine. So the relationship between wind speed and power output is usually described by this wind power curve here. So here is just the example for illustrating wind power curve. You can see there are three speeds here. The cut-in speed, that is the speed, that's the point where the blades start to rotate, power start to generate. If the speed is anywhere below there, well, the turbine will not turn. Okay, you need enough speed for the turbine to rotate. And the cut-out speed, that's a point where the wind is too strong. The wind turbine has to shut down in order to avoid damage. The rated speed is the speed that can produce the maximum power output. Okay. And all these speeds are related to the turbine design and size. And once you have the turbine, there's nothing you can do about the power curve. All right, so with some basic knowledge on wind power, let's look at the wind speed index that we're going to use. We consider two indexes. Both of them have been considered in the literature. The first one is the sum of average daily wind speed between the cut-in and cut-out speeds over the period of T0 and T1. So you can see that here, this one here is an indicator function, and L is cut in, U is cut out. Okay. And WT is the average wind speed at the turbine height during period T. The second index here is the sum of the daily average wind speed over the period. This one is the simple sum of WT. The CWSI represent cumulative wind speed index. Well, since the turbines operate between the cut-in and cut-out speed, you can see that the first index would be a better indicator of wind power production, right? Okay, so we're going to consider both future and option. This slide is very standard. Payoff, future option payoff. Okay, K is option strike price, F is the future price, and we assume that at time T, the wind energy producer will enter a derivative contract written on the wind speed index accumulated over the period of T0 to T1. And at expiration T1, the derivative payoff will be made to the producer. So that there is this future payoff and put payoff. They're all related to the wind speed index. Because as a wind energy producer, you would want to hedge the uncertainty in wind power production. If you enter these derivatives, you would want to short the future or long the put. Right, so now let's look at some wind speed modeling. So we know what kind of index, what kind of derivative we're going to use. Wind speed modeling is obviously very important for the price. We obtained the hourly mean wind speed at the Virgin Weather Station during 2017 to 2021. It's 5 years of data. If you want, you can get longer period. And the Virgin Station is located in a German state. I'm not going to try to pronounce that. The German state with the highest number of turbines and installed wind power capacity. And so if you look at the time series plot on the left side, you will see this strong seasonality. You basically see the waves, right? And you look at the right-hand side, you see that skewness in the histogram. Just to have a better view of the seasonality, I plotted the average wind speed on the same day of the year in 2017, during 2017 to 2021. So this is, if you look at the plot there, the red line is the lowest line. Well, you can see that in winter time, the wind is stronger, right? So if you look at here, the wind is stronger in winter times and lighter in summer. And you also see the volatility, the seasonality in the volatility. So in winter time, the wind has higher volatility, right? In the summertime, it's lower. So you do see seasonality in both the value and the variance. Okay, well, it's more difficult to visualize the volatility clustering. So we ran a test after initial fit to check for volatility clustering. All right, so we're going to capture the features of wind speed, use a SAR S-gauge model. S represents seasonal. WT, that is the wind speed, is the sum of mu t, that's the unconditional mean of the wind speed at time t, and yt here is the demeaned wind speed. Okay, and yt is assumed to follow a ARP model, so we can capture the serial correlation. And epsilon t here is the error term, and sigma t, that is the volatility at time t. And zt here is a variable with mean 0 and variance of 1. Okay. How do we incorporate the seasonality? Here's the slide. So we'll try to incorporate seasonality observed in the mean and variance by Fourier series. So if you look at the unconditional mean mu t, we have a constant C0, and then this part, these two terms is actually the Fourier series. Okay, so R here is the number of terms summed in Fourier series. And similarly in the volatility in the variance model, okay, since we want to capture the volatility clustering, so we're going to use a gauge model, gauge UV. So you can see the arch-gauge terms here. In addition, we have the Fourier series as well in the variance in the volatility model as well. Okay. So by doing so, we're able to capture all the seasonality and also the heteroscedasticity. How do we estimate the model? Well, Campbell and Diebold in 2005, they estimated a similar model for temperature using Gaussian quasi-maximum likelihood. Okay. The argument for using a Gaussian QML is that an earlier paper found that the bias of using the QML estimates is relatively small when the true data is t-distributed. Okay. But that earlier paper also warned the bias and the variability of the estimates tend to increase with the degree of heteroscedasticity and excess kurtosis. In addition, in the wind speed, we observe very strong skewness as well, right? So what's the impact of skewness on the bias of the estimator? We don't know. That's why we thought that it's very necessary to investigate whether this QML is suitable for our data. And we also want to consider alternative distribution assumptions. What is a proper distribution for this kind of data? Okay. And what we came up is the generalized hyperbolic distribution. This is a distribution that allows you to capture skewness and excess kurtosis. So we consider generalized hyperbolic distribution and its two special cases, hyperbolic distribution and normal inverse Gaussian distribution. So we're going to call it NIG from now on. The generalized hyperbolic distribution has been used in the financial literature. It has been shown to provide very good fit to daily stock return, which exhibits the excess kurtosis. And it's a very flexible class of distribution because it nests a number of well-known distributions, for example, hyperbolic, NIG, student T, variance gamma, and normal distribution. Okay, so normal is actually a special case of, it's like a limit case of the generalized hyperbolic distribution. Okay, so this is the probability density function. Well, you don't need to know it. It's not very important for the purpose of this presentation. All you need to know is that this distribution has 5 parameters. Okay, the alpha, beta, delta, mu, they are the shape, skewness, scale, and the location parameters. And the lambda here, if you have a special value for lambda, usually it corresponds to a special case of the generalized hyperbolic distribution. So if you set lambda to -½ then you get a normal inverse Gaussian distribution. If you set lambda to 1, you get a hyperbolic distribution. If I remember correctly, if your delta goes to 0, you get the variance gamma, something like, you can see how it nests all those distributions we just talked about. And since here we're going to use generalized hyperbolic distribution for the ZT we saw earlier, just go, oh, not here, just go back here to remind you what is ZT. So ZT is here. So that is a distribution with 0 mean and unit variance. So we will have 2 constraints on the parameters to ensure 0 mean and unit variance. So we can reduce the number of parameters by 2. All right, we're going to use maximum likelihood method to estimate the SAR S-Garch model with the generalized hyperbolic distribution and the special cases. Well, before we go to look at the model estimates, well, we want to select the orders for our SAR and S-Garch. So I used the QML to estimate these models, the SAR S-Garch models with different numbers of Fourier terms, AR order, arch, and Garch, and then choose the model with the lowest AIC. So the selected model has AR2 in it, and 1 sum of Fourier terms in the mean and 1 in the variance. And we also use the Garch 1, 1. So this is the selected order for our SAR S-Garch. And now let's look at the parameter estimates when we use the Gaussian QML and the maximum likelihood with generalized hyperbolic distributions. So when you use Gaussian QML, I simply put the normal assumption here. So put normal here. If you compare NIG, hyperbolic, generalized hyperbolic, these three columns, you won't really see much difference. They're very close. Well, the difference, you can see the difference in the parameters for the distribution, which is expected because we do have lambda set to different values. Well, for NIG and hyperbolic. For generalized hyperbolic, this lambda value is optimized. Okay. But if we look at compare normal and NIG, the first 5 parameters here, they are related to the mean, and the next 5 are related to the variance. Okay, so if you look at the parameters related to the mean, you will see that A1, that is the coefficient in the AR model, the first flag order. There's quite a bit of difference depending on whether you use normal or NIG. And if you look at the parameters in the variance, well, the difference is also quite large in each of the parameter. Okay. So what does that mean for our wind speed prediction? We'll talk about that very soon. Right. And if you look at likelihood, well, we do get much better likelihood, maximize likelihood by using generalized hyperbolic and the 2 special cases. Well, it's clear that if you compare AIC, the hyperbolic would be a winner. We also wanted to look at the standardized residuals to see if, to do some analysis on the residuals as well. So I plotted the kernel densities of the standardized residuals. You can see this as a empirical distribution of the standardized residuals. You don't see much difference actually between the 4 distributions. So using QML, your parameter estimates, you do see a lot of difference, but the standardized residuals, the difference is quite small, I would say, compared to what we saw in terms of the parameter estimates. When you learn your linear regression, we will say that you want to check your residuals to see if it follows a normal distribution, right? So let's check our residuals to see whether the empirical distribution matches with the assumed distribution. And here's what you will see. If we look at, let's say this one here, the first one for normal, the dashed line is for the kernel density, so that's the empirical distribution for the standardized residuals. And the solid line is the standard normal, that's what we have assumed. You'll see the large discrepancy between the 2 curves. But if you look at, say, NIG here, well, the kernel densities actually matches the estimated densities matches the kernel density pretty well, except that the peak is a little bit higher. Okay, that's the same thing with hyperbolic and generalized hyperbolic. So you can see that normal is clearly not a good choice, right? But that's the one that has been used so often in literature. Now we have our estimated model. We're gonna do some simulation of future wind speed at turbine height. So we considered 2 methods. One is parametric. So we have our distribution assumption. We have our estimated parameters. Let's first simulate from the estimated parametric distribution, then determine the simulated wind speed based on the SAR Escarch model. Right? This is very standard. And the second method we're going to use is semi-parametric, that is going to be used with the QML. The idea is that when you fit the QML, you're thinking that I don't really know the true distribution of the data, so I'm using the quasi maximum likelihood, pretend it's normal, right? Now, in order to capture potential features in your residuals, we're going to use the bootstrap to resample from the standardized residuals. And hopefully that will help us to reduce some of the errors from using the quasi maximum likelihood. Well, the idea sounds really great, right? Let's see if it works. Okay, so these are the densities, the kernel densities of simulated wind speed at turbine height on March 31st, 2022, under different distribution assumptions. The vertical lines represent the mean values. So if you look at the right-hand side first, well, not a lot to see. Oh, this one. The right-hand side, they are all like generalized hyperbolic NIG. The kernel densities are very close, and the mean values are very close. You just see them overlapping with each other. Not sure if you can see very well this one. So I have the solid line, that is the bootstrap, the semi-parametric method, and the dashed line, that is the normal, and then the dotted line, it's very faint, that's the hyperbolic. If you look at the mean value, they are actually quite close. But if you look at the distribution, there's a lot of difference there, right? So the normal is clearly having a much larger spread. Well, if you use hyperbolic, a lot, like the variance would be much smaller, much smaller spread, and you can see the skewness as well. So if you are looking at an index that only cares about the mean value, then you'll be fine. Using normal, that's okay. But if you're using an index that depends on the shape of the density, say, for example, your index only care about, say, this part of your curve or this left side of your curve, you might see a lot of difference when you do your pricing, right? Okay. All right, that's the wind speed model. Now let's move on to the pricing method. What we're going to use is the conditional Escher transform. Escher transform was first introduced by Gerber Zhou in 1994 for option pricing. And the use of Escher transform has been justified by many researchers. The conditional Escher transform is proposed by Bowman as a generalization of Escher transform to serve a more general class of stochastic processes. We have seen conditional Escher transform used to price derivatives that follow Garch model with, say, gamma distribution or normal distribution. So the purpose of the conditional Escher transform is really to give us the risk neutral measure. Just one thing related to this, I've learned the change of measure from David when I was a student. So if you see some error on the slide, you know whose fault that is. Don't feel nervous. I double checked the slide. So here we're going to have the XT, that is the process adapted to the filtration FT. FT would have all the information up to time t. We denote the conditional moment generating function of XT with respect to the filtration at t-1 by this MP. So P means the real world P measure. We also define the process capital ZT, which is actually a product of a series of Escher transforms, because this is an extension of Escher transform. It's easy to see that ZT here is actually a martingale. See the T, that is what we call conditional Escher parameter, and it is a FT-1 measurable process. Okay, it's okay if you don't get it. That's all right if you're not into the risk neutral pricing. That's all right. We're just briefly talk about this. The conditional Escher transform Q with respect to P. So Q would be the risk neutral measure, the risk neutral world of the process can be defined by this Redon-Nikodym derivative, which is exactly ZT here. Okay. I'll be just very brief with the conditional Escher transform. Conditional Escher transform is very versatile. It can be applied in a Garch framework for any type of distribution, as long as the moment generating function exists. So it's good. You can also write out, you can also express the conditional moment generating function of xt under q by the ratio of two conditional moment generating function under p. Okay. This formula is going to give us the risk neutral dynamics later on. In option pricing literature, xt usually represents the log stock return. And we can find as theta t, we usually set theta t to the solution of this equation here. So what this equation says is, well, in the risk neutral world, if you invest $1 in the stock, the expected amount you receive at the end of the period should be exactly the same with the $1 invested in the risk-free bond. Okay, so that's like that's a no arbitrage. But when we think about wind speed index, it's not a tradable asset. We cannot impose this condition. So here we took a very simple approach. We assumed theta t to be just a constant. Well, in the future research, we would want to calibrate theta t using observed wind derivative prices. Okay, so we've looked at the wind speed model that is under the real world measure under P. The mean and variance of the conditional variable, you can easily write it out. The mean would be, I set it to AT, that's the unconditional mean plus the sum of the AR terms. Variance is sigma t square. And for each distribution assumption, we can actually derive the distribution of the conditional variable under Q. So it's very easy. So here's when you assume normal distribution, here's your risk neutral dynamics. Well, I'm not going through the details to bore you, but you can write out the risk neutral dynamics very easily. Okay. And here, if you have ZT follows a generalized hyperbolic distribution, you can also write out the risk neutral dynamics out very easily. Using the conditional Escher transform under Q, if you assumed normal under P, you will still get normal under Q, but just get different parameters. If you use generalized hyperbolic distribution under P, you will still get generalized hyperbolic distribution under Q, but again with shifted parameters. Okay. So that's the pricing method we're going to use. That's how we generate the risk neutral dynamics. So this slide here is showing you the simulated wind speed indices under Q. So what does the distribution look like under Q? If we look at the top panel, I have three plots on the top panel, right? Each of them correspond to a different value of theta. So you can think theta as market price of risk. As theta gets more negative, the investor would demand more premium. So you can see that as theta gets more negative, the curve will shift more to the left. Okay. Let's look at theta equal to 0. When theta is equal to 0, that simply means under P, under Q, you don't get any difference. Okay. Let's look at the difference between these three distributions we talked about, normal, hyperbolic, bootstrap. I'm not sure if you can see very well, but you do see the difference between the curves, right? So the solid one, that is the normal, and the dashed one, that is the hyperbolic. So you can see that normal has a much smaller, much larger mean value here, the vertical line, compared to the mean value for the hyperbolic. This is the simulated index value for CWSI1 that is related to cut in, cut out speed, the index related to cut in, cut out. So if you're going to price a derivative on this index, you would expect a lot of difference in your derivative price if you use different distributions, right? And now, if we look at the bottom panel, these are the simulated wind speed indexes. Index for the simpler one, that is the sum of the wind speed. And for this one, you don't really see much difference in terms of the mean value, right? And what you see is that the spread is different. The normal has a larger spread, hyperbolic has smaller spread. If your focus, well, not if you, your focus here for the second derivative is really actually the mean, because you're summing the WT. So as we saw earlier, when you look at the simulated wind speed under P, the mean value was very close, depending, doesn't matter which distribution you use. So that's why you get the similar mean value here as well. So if you have a derivative, say future, that's simply depending on the mean value, then you won't see much difference, right, in terms of price. But if you are looking at an option which maybe only looking at this part of the curve or the right tail of the curve, then you would expect a lot more difference. Okay. So let's move on to the pricing approach. So we've talked about how we generate the risk neutral dynamics of the wind for the wind, right? In terms of calculating the price, we have two approaches. The first method is suitable for the parametric wind speed model. So we're going to just simulate n passes from the risk neutral dynamics that we derived earlier. And then you calculate the derivative payoff, simulated derivative payoff, you discount it to current time, and then you do the average to get your derivative price. That's all under Q, under the risk neutral measure. So this approach is efficient and easy to use when the risk neutral dynamics are known. You can write it out, you can simulate it. Well, the second approach is suitable for both parametric and semi-parametric wind speed models. So instead of simulating from Q, risk neutral dynamics, now we're going to simulate from the real world dynamics. That is the one under P, the first wind speed model we were seeing. Okay. So you would simulate the wind speed under P and calculate the index value under each simulated pass, calculate derivative payoff, discount to current time. In addition, you will want to multiply this random Nicodemus derivative, compute it based on the ice pass of the wind speed dynamics under P. So this is how we do the change of measure here. Yeah. So we're not looking at neutral dynamics. Instead, we look at real world dynamics, but we do the change of measure here. Okay, then you take the average. So if you use this method, you don't need risk neutral dynamics. This is really good because sometimes you are not able to derive analytic formula for risk neutral dynamics if you have very complex structure. Or when you have this semi-parametric wind speed model, you do the bootstrap, you don't have any model, right? And you can use the second pricing approach. Okay, our pricing results. So we're going to look at the prices of derivatives on both index. The first one is future, the second one is the put. For the put option, we have the strike. The strike is set to the median and 25 percentile of the realized wind speed index values in the past 10 years. And the index period is the first quarter of 2022. Okay. And the risk-free rate is set to 4%. Now let's look at this table here. It's a rather large table. So this table, we are looking at the prices of derivatives written on the first index. So the first index is the one that's related to cut-in and cut-off speed. Okay. Okay, let's first look at the future here. So you can see I have two methods. Method 1 simulating under Q, method 2 simulating under P. When I have the theta equal to 0, well, the two methods shouldn't make any difference because Q and P is exactly the same. Just to verify it, you get exactly same value under normal and normal here. Okay, that's good. And if you look at theta equal to negative 0.05, hey, let's compare method 1 and method 2. You can see there is a small difference, which is expected. The difference is fairly small if you look at all these values, compare these values under normal and this column here. They're fairly close. Okay, so that sort of verifying our two approaches, our second approach should work. Okay. If you compare normal and hyperbolic, you'll see the large difference between the prices. So if you have normal, your future value is a lot larger than the hyperbolic, which is expected because when we looked at the density curve, we saw that the normal distribution had much larger mean value, right? And if you look at put option, well, because of the payoff is K minus index value, so you would expect normal to have smaller price for the put option. All right. Well, we had the hope that the semi-parametric method, the bootstrap, would help in some way reducing the pricing error, right? Let's see if it works. So the bootstrap, we have, let's compare here. I have 106, which is slightly lower than normal, but still a lot higher than hyperbolic. If we think hyperbolic is, well, it's not perfect, but maybe it's closer to the ideal distribution, right? If we think hyperbolic is the right distribution, obviously bootstrap is a lot worse, but marginally better than normal, right? And yes, that's what we see here. So the bootstrap, we had the hope that when you use this semi-parametric model, you use the QML plus bootstrap, we would be able to capture those skewness, kurtosis, but it looks like it's not working very well here, right? The similar thing is happening with the put option. So we see this large difference between the prices using normal and hyperbolic. And the bootstrap helps somewhat, but not so much, a little bit. So a small amount, I would say. Okay. Same thing when you look at a smaller, lower strike price. Okay, so that's the first index, which is related to cut in and cut out speed. And now if you look at the second index, that is the index that's simply the sum of wind speed, right? If you think about the density curve we saw earlier, when you use different distributions, we had the very close mean values, but the spread was quite different between normal and hyperbolic. So in this case, if you look at the price under normal and the price under hyperbolic, you'll see that the difference is quite small for future here, right? Because future price is really just about the expectation under the Q, if you think about simulating under Q. And if you look at here, let's see how the bootstrap, the semi-parametric approach work. Well, it's actually worse. So normal and hyperbolic have quite close values. Bootstrap is a bit higher. This is because if you go back to the distribution, it's not very clear, but if you zoom this one up, you will see that the bootstrap has slightly larger mean value than normal and hyperbolic. Well, this is just for one day, because we are looking at cumulative wind speed index. You're adding all the differences over 90 days. So in the end, you will see a bit larger difference in the future price. Okay, you see similar thing for put option. Okay, same thing. Normal and hyperbolic very close to each other, and bootstrap got a bit lower prices because it had the larger mean value when you look at the index. And finally, if you look at the last one, this put option with K set to the 25th percentile, magically, bootstrap is working quite well in the last one. Why is that? Well, let's go back to that density curve. Here, K is 201. That's the 25th, oh, not here, percentile. So if you look at 25th percentile, let's say you look at here, let's just look at theta equal to 0, it's easier. So if you look at 200 is around here, 200. If you're looking at the put with strike 200, and then, well, only the curve that's under 200 will give you the positive payoff, right? So if you look at this curve closely, you will see that normal distribution has much larger probability of having values below 200. So that means for normal distribution, you have, well, more chance of generating positive payoff here. So that's why it gives you a higher payoff for put, a higher price as well. But if you look at hyperbolic and bootstrap, they actually have very close shape at this level, at the left tail. So that's why they produce very similar price, the hyperbolic and bootstrap. Okay, so as we can see, the bootstrap, the semi-parametric approach, which we had a hope for it. It works sometimes in reducing pricing error, but it's not always. It really depends on which part of the curve you're looking at. In some part it does quite well, some part it doesn't. And the other thing we noticed is that if you have a derivative written on the second index, it's much more tolerant of the model risk. So it doesn't really matter which one you choose. The difference is actually quite small. But when you have the first index, which is related to the cut-in, cut-out speed, well, the model risk can be quite significant. Well, what happens in reality is that the wind power future is related to the power curve of the wind turbine, which means it is related to cut-in and cut-out speed, right? So if you're going to use normal distribution, you will likely have a quite large pricing error in there. Okay. So using the correct distribution is really important. All right, conclusion. We have proposed the models to capture the stylized effects of wind speed. We found that the generalized hyperbolic distribution is well suited to capture the skewness and excess kurtosis in wind speed. We've used the conditional Escher transform as the pricing approach. Well, we consider the wind speed derivative. It's very simple, but you can easily extend the conditional Escher transform to price the wind power future. For example, the future written on Narax wide, which is essentially a function of wind speed. So you can use the same approach, really. We found that the difference in parameter estimates using normal distribution and generalized hyperbolic distribution is very significant. And the pricing error can be quite high when you're looking at the index that's closer to the power curve related to cut-in and cut-out speed. So since the actual future is written on the Narax wide, which is related to the power curve, you would expect the model risk to be very significant in reality. And final point, the semi-parametric approach doesn't seem to work very well, although we had a high hope for it. But that's just the reality of research. It just doesn't work sometimes. Okay, and that will conclude my presentation. Thank you very much.